I welcome you to the channel which explores the intellectual content for the benefit of students, faculty, and industry professionals. Let us try to discuss when a researcher should use simulation approach. I am Professor Jitesh J. Thakkar, Dean Academics and Professor Logistics and Supply Chain Management at Gati Shakti Vishwavidyalaya, Central University, India's first and only university in transportation and logistics sector. I was a professor at IIT Kharagpur in the domain of logistics and supply chain management. Let me introduce you to the channel, Professor Dr. Jitesh J. Thakkar. At present, this channel comprises two playlists. One is faculty and student development, and the other is logistics, supply chain, and infrastructure projects. You can scan this QR code on the right side to explore the intellectual content on this channel, benefiting students, industry professionals, and faculty. About the playlist, faculty and student development. This domain, faculty and student development, is multifaceted in nature and it requires the grooming on various dimensions, broadly, teaching, research, and experiential learning. The aim of this platform is to address how faculty and students can respond to evolving educational needs and challenges in interdisciplinary education as expected by new education policy NEP 2020. The platform shares the content in broadly three domains for the 360-degree development of the faculty and students in higher education institutions. Number one, enhancing teaching effectiveness using improved pedagogical skills, innovative teaching methods, classroom management techniques, student engagement strategies. Number two, utilize educational technology. Number three, foster critical thinking for solving complex problems. The second broader area within the faculty and student development is promote research, excellence, and productivity by providing training in research methodologies, data analysis, and scholarly writing. And number three is enhance experiential learning through projects, internships, and exposure to real-world problems. This platform explores critical dimensions of faculty and student development for enhancing the capability and quality of the most important stakeholders of higher education system, faculty, and students. To begin with, I would like to introduce my university, Gati Shakti Vishwavidyalaya, which was created as a central university in 2022 by the Act of Parliament. GSV is established by Ministry of Railways, Government of India, and this university has a unique mandate to create a best-in-class resource pool for the entire transportation and logistics sector, including rail, road, water, aviation, ports, and shipping across technology, that is infrastructure, management, that is services, and policy, that is regulation, comprising multidisciplinary teaching, research, executive training, and skilling. It follows a demand-driven curriculum to meet the industry needs of transportation sector, high-quality faculty with global exposure, and leveraging state-of-the-art infrastructure of centralized training institutions of Indian Railway sets a perfect pitch to excel for Gati Shakti Vishwavidyalaya. GSV is propelling the nation towards a new era of interconnectedness and sustainable development through innovations and best practices in transportation and logistics sector. The vision of the university aligns the need of 21st century and the requirements of transportation and logistics sector, and it is innovation-led, industry-driven university. Broadly, the mission of the university includes best in the world futuristic education and research, effective collaboration with industry and various stakeholders, and imbibe and internalize professional work ethics and culture to foster lifelong learning paradigm for a developed India. Academic programs, we are offering the programs under both category for regular students and for working professionals. BTech in civil engineering with specialization in rail engineering, BTech in electronics and communication engineering with specialization in rail engineering, BTech in mechanical engineering with specialization in rail engineering. So students would study all the core and critical aspects of their respective domain, that is civil, mechanical, electrical, electronics. In addition to that, they will have 15 to 20% specialized courses in the domain of railway engineering or transport engineering broadly. BTech in artificial intelligence and data science with specialization in transportation and logistics, BTech in aviation engineering, MBA in logistics and supply chain management, MBA in ports and shipping logistics. The program is jointly offered with Indian Maritime University. For working professionals who are studying in the hybrid mode, this means 80% of the content they study in online real-time mode, and for 20% of the content they come for the campus immersion. So MTech Intelligent Transport System, MTech Railway Engineering, MTech Bridge and Tunnel Engineering, MTech Roads and Highway Engineering, MBA Logistics and Supply Chain Management, MBA Metro Rail Management, MBA Multimodal Transportation, MBA Aviation and Operations Management, PhD in Engineering and Management with a special focus on transportation and logistics sector requirements. So the university offers a complete portfolio to cater the different challenges in all the modes of transport. For regular students who are the future leader in this transport and logistics sector, and working professional, they undertake the program for their upskilling and reskilling in the domain of transportation and logistics. This video exchanges the views on when a researcher should use simulation research approach. Simulation is quite a versatile approach. It mimics the reality and handles the complex system which otherwise is difficult to investigate with the real-time experimentation or using the mathematical and analytical models. So let us see under what situation researchers should opt for the simulation approach. So broadly, if we look into what is simulation, then simulation involves the construction of a dynamic computer-based model which represents a real-world process. This representation or model is designed to mimic the essential characteristic and behavior of the system which is under study or investigation. It may be an engineering system, it may be the physical system, it may be the situation or the system in the domain of management. So simulation can help us to model all sorts of different kind of situations. Through controlled experimentation with this simulation model, researchers can explore systems responses to various input scenarios and permutations. This exploration allows for the observation of complex interactions, the testing of hypotheses, and the prediction of outcomes in a safe and controlled environment. So many times it's not possible to conduct experimentation in the physical mode, and as a precursor we may like to go for the simulation for the safety reason, to handle the complexity, and also to respect the budgetary and time constraints. So simulation acts as a surrogate for the real system, enabling researchers to investigate phenomena that might be too costly, dangerous, or time consuming to study directly. It can also be used to explore hypothetical scenarios or to optimize the performance of existing system. And typically, simulation allows for the analysis of the systems with a very high degree of complexity where analytical solutions may be difficult to deploy. Simulations output data can then be analyzed using statistical methods for their statistical validity and draw the conclusion and generalize the insights that can be applied to real world systems. In a very simple way, simulation is the next best thing to observing a real system. It deals with a computerized imitation of the random behavior of a system for the purpose of estimating its measure of performance. If we look at the broad classification of the simulation, then it is divided into two categories. One is stochastic, other is deterministic. Under stochastic, we have the static simulation and dynamic simulation, and further, dynamic simulation can be classified into discrete and continuous simulation. Similarly, you have deterministic simulation or system models, which can further be classified into static and dynamic. And under dynamic, we can have discrete or continuous simulation models. Let us try to appreciate this with some examples. So if you look at the stochastic simulation, then it incorporates the randomness, uncertainty. Typically, the examples include Monte Carlo simulation, Markovian chains, and models for financial analysis, investment returns, and maybe the epidemic spread. Couple of examples, let us say in the domain of financial modeling of stochastic simulation, I can apply the Monte Carlo simulation to model investment portfolio, analyze risk. The stock market is always under dynamic situation, stochastic situation, and I can estimate the potential returns by simulating various scenarios based on the probability distribution of the stock returns. Stochastic volatility models, these are used to capture the volatility of the financial assets, which can fluctuate randomly over time. The other category of simulation model is this deterministic simulation model. And typically, deterministic model predicts the outcome with certainty given specific inputs without any random variation. Couple of examples of deterministic simulation models include, let us say, financial models, investment return calculations, predicting the future value of an investment based on the fixed interest rate and compounding period. For example, you are investing in the fixed deposit. Cash flow modeling, projecting future cash flows with a pre-specified discounting rate based on known or assumed inputs. Budget forecasting, estimating future expenses and revenue based on fixed assumptions. So we are not accommodating the uncertainty here. Engineering, you can do the structural analysis, predicting the behavior of a structure under known load conditions. Fluid dynamics, simulating the flow of fluids under the specific conditions. Inventory management, typically a very critical problem in the logistics and supply chain management. So modeling the accumulation of inventory, typically when we talk about the bullwhip effect and the accumulation of the inventory across the supply chain, so this can very well be modeled as a deterministic simulation model and accumulation of inventory at constant rate to meet the deterministic demand. There could be other examples like social media influencer growth, predicting the number of followers a social media page will gain based on assumed follower growth and churn rates, and weather forecasting, predicting the weather based on known atmospheric conditions and simplified models. Let's look at the other category, that is static simulation. Static simulation model, which represents a system at a specific point in time without considering change over time, including things like calculating total weight a ship can carry, demand and supply analysis for market, break-even analysis for calculating output levels, and so on. Some of the examples of static simulation include calculating the total weight a ship can carry. It depends on the ship structure and capacity at a given time. Demand and supply analysis for market equilibrium. So here I would like to consider supply and demand balance without considering the change over time. Break-even analysis for calculating output level, object model diagrams, set of algebraic equations where each output is a function of the inputs with no consideration of time or history. Static models in engineering could be analyzing structures, bridges, or buildings under static load, and static model in economics. We can use this model for analyzing the market equilibrium or resource allocation in a given state. Similarly, we can look into the dynamic simulation. So, dynamic simulation model systems behavior over time, allowing for testing different scenarios and conditions. An example could be weather forecasting, flight simulators, car crash modeling, simulation of biological systems, and manufacturing processes. So, a couple of examples of dynamic simulation in engineering and manufacturing includes process control. So, I want to capture the dynamic behavior of chemical plants, refineries, or other industrial processes and optimize the operations, control systems, and safety measures. Product development, simulating the performance of products like cardiovascular stents or other medical devices under various conditions of flow of blood and medical history of the patient, such as transient pressure loading, to optimize design and performance. Manufacturing processes, modeling and simulating manufacturing processes like batch, distillation, or other dynamic processes to understand and optimize their behavior. Mechatronic systems, simulating the behavior of robotic arms, mass spring damper systems, hydraulic systems, and other mechatronic systems to test control algorithms and optimize their performance. So typically, the process of simulation in general goes like this. You define the problem, introduce important variables, construct simulation model depending upon the situation you are analyzing, whether it is a static or dynamic, stochastic or deterministic. Specific values of variables to be tested. Based on the history, you may define some ranges or the values for the variables. Conduct the simulation for the intricacies of the system-specific variables. Examine the results. You may like to conduct the statistical test to examine the simulation results and select best course of action. So typically you are doing what if analysis, and then based on the various scenarios generated, you can take the rational and sustainable decision. So let us have a deep dive into the core issue where a researcher should use a simulation approach. So I would like to cite a couple of examples and the situations where simulation becomes the most beneficial, inevitable approach. Number one, real world experiments are impractical, impossible, or unethical. Typically, in the medical science and many other domains, it is unethical. So, high cost or risk are involved. My experimentation is expensive, time consuming, or dangerous. Ethical considerations like manipulating variables in a real world setting might be unethical or pose risk to participants. So, typically, the medical science, they cannot all the time experiment on the human being or other creatures and manipulate their variables. So some of the examples testing the effect of a large-scale natural disaster on a city's infrastructure, evaluating the impact of a new economic policy on a national economy, simulating the spread of a highly contagious disease. The other situation, second situation, is studying complex system with interacting components. You just think about the body and your heart, liver, kidney, intestine, brain, all these organs are interacting with each other, and there is a high degree of non-linearity, complexity, interdependency involved. So dynamic interaction system being studied involves multiple components that interact in complex and non-linear ways. I gave you the example of human body. Difficult to predict outcomes, challenging to predict the system's behavior through analytical methods, and for example, modeling traffic flow in a city to optimize traffic light timing. Simulating the behavior of financial market to assess investment strategies, and modeling climate change to predict future environmental conditions. All these are the situations in which it is absolutely impractical to go for real life experimentation, and simulation becomes inevitable. The third situation, when you are interested to examine or explore what if scenarios and testing different strategies. So you want to compare the potential outcomes of different decisions or interventions, and typically you want to identify the best strategy for achieving specific goals. For example, you want to simulate the different supply chain configuration to minimize cost and maximize efficiency. Absolutely, it is not possible to do it in a real life world and then understand the cost, profit, inventory implications. You have to go for the simulation approach. Testing different emergency responses, plans to improve disaster preparedness, and simulating different manufacturing processes to optimize production output. The fourth situation in which simulation becomes highly relevant, understanding the system behavior over time. So, dynamic process, you want to study how a system changes or evolves over a period of time. Today it is 2025, and I want to predict the system behavior and the output maybe 10 years down the line in 2035. So it's absolutely only possible with this simulation approach. So modeling population growth and its impact on the resource availability, as I said, 10 years, 20 years down the line, simulating the spread of information or innovations through social networks, and modeling the long-term effect of climate change on the ecosystem. The fifth domain where simulation has a great advantage is training and education. Safe learning environment. Simulation can provide a safe and controlled environment for training individuals in complex tasks or decision making. For example, flight simulators for pilot training, medical simulations for training surgeons and other healthcare professionals, business simulation for training managers and executives. And you just think that virtual reality, augmented reality kind of simulation can help many workers and operators to be trained for safety. Let us say they are working in the chemical plant or they are working in the steel plant where highly hazardous environment prevails, and it's very difficult to train them on real time system setting. They can be immersed into the virtual reality, and the simulation can help them to acquire the necessary safety precautions and a sense of, say, urgency for the different kind of situations. So broadly, types of simulations include discrete event simulation. One of the example is customer arrival at a store, continuous simulation which models the system where changes occur continuously over time, fluid flow in a pipe, agent-based simulation models the behavior of individual agents and their interaction within the entire system. So agent-based simulation has gained significant attention in modeling, simulating various scenarios in logistics and supply chain management, where various parties like third-party logistics, fourth-party logistics, contractors, or maybe transport service providers and many other agencies are involved. By considering the situations and types of simulation, researchers can determine when this approach is most appropriate and effective for their research needs or the context they are investigating. So broadly, Simulation-based research is used across many fields to model complex systems. It can be engineering, it can be management, social science, and processes, allowing researchers to study scenarios that are difficult or impossible to investigate in the real world. Let us look at a couple of real life problems where simulation has been successfully deployed, used, and the concerned researcher or the organization has received highly advantageous outcomes. So first is the transportation and logistics domain. Traffic flow simulation is one of the most promising area, and typically simulating traffic flow in a city to operate the traffic light timing, road design, and public transport route. This can help to reduce congestion, improve travel times, and reduce the pollution. The second area is supply chain simulation, modeling a supply chain to identify bottlenecks, optimize inventory levels, and evaluate the impact of disruption, natural disasters, supplier failures, and so on. The third domain area in the transportation and logistics where simulation is highly useful is airport operations simulation. So simulating airport operations, including aircraft movements, passenger flow, and baggage handling to optimize resource allocation, reduce delays, and improve passenger experiences is highly explored, and simulation benefits are realized. The second domain where simulation has shown remarkable benefits is the healthcare. For example, epidemiological modeling, simulating the spread of infectious disease, for example, predict outbreaks, evaluating intervention strategies, vaccination campaigns, social distancing, and inform public health policies is one of the area where simulation is widely used. Hospital operation simulation. So today there is a huge patient flow, and unless really you simulate this flow, you cannot get into the waiting time details and provide the appropriate allocation of the resources. So modeling patient flow in a hospital to optimize resource allocation, reduce waiting times, and improve patient care is another area where simulating emergency room operations, operating room schedules, and bed management are highly critical. Surgical simulation. So using virtual reality or computer models to simulate surgical procedures and train the surgeons and practicing complex operations. The third area is environmental science and ecology. So climate change modeling, you want to predict, simulate the Earth's climate system, predicting future climate conditions, assess the impact of greenhouse gas emission, and evaluate mitigation strategies. Ecosystem modeling, so modeling the interaction between different species in the ecosystem and understand the population dynamics, predict the impact of environmental changes, and inform conservation efforts. Hydrological modeling, simulating water flow in rivers and watersheds to predict floods, manage water resources, and assess the impact of land use changes. The fourth domain where simulation is highly used, most advantageously applied is finance and economics. So financial market simulation, typically you are simulating the behavior of the financial markets to test investment strategies, assess risk, and predict market crashes. Economic modeling, modeling national or global economies to analyze the impact of economic policies, predict economic growth, and understand the economic cycles. The fifth major area where simulation is widely used in real life problems is manufacturing and engineering. So certainly if you look at the petrochemical industry and other processing industries, then manufacturing process simulation, typically to optimize production schedules, reduce cost, and improve product quality is highly advantageous. Product design simulation. So we always say quality must be at the design stage. So using computer-aided design and simulation software to test the performance of new products under different conditions before they are physically built or launched to the market. Structural simulation, simulating the behavior of structures like bridges, buildings under different loads and conditions to ensure their safety and stability. The sixth domain where simulation is highly useful is military and defense. War gaming. You cannot really do it when the war occurs. So, simulating military operations and train commanders, evaluate strategies, and analyze potential outcomes of conflict. There are many variables involved. Your war strategy, your military forces, the integration among three different forces of defense, air, army, and navy. And in addition to that, you are using the different kind of arms and ammunitions. Flight simulator, using flight simulator to train the pilots in a safe and controlled environment. So broadly, if we see the key characteristics of the simulation, then it involves the modelings of the complex system and typically try to depict the behavior of the interaction of real world system. It helps to conduct the what-if analysis, to explore different scenarios and test impact of various interventions or changes. It captures the dynamic behavior, how systems change and evolve over a period of time, and various computational tools or softwares are useful to conduct such kind of simulation-based study. Let us look at the case study which has remarkably been benefited, which is optimizing port logistics with simulation. So if you look at the context, then ports stand as intricate hubs, orchestrating a symphony of interconnected elements, and this demands precise arrival and departure of diverse vessels, the swift and efficient operation of towering cranes, the ceaseless flow of trucks and trains, and the strategic management of expensive and expansive storage facilities. In the globalized economy, typically the efficiency of this port is not merely desirable, but a critical determinant of economic competitiveness, and typically it has a significant impact on your supply chain and different logistic dimensions and consumers. Congestion within port is quite a common phenomenon and it directly translates into substantial financial losses stemming from increased operational cost, missed delivery deadlines, diminished customer satisfaction, and so on. It has a great impact on the entire region and national economies. Ports are dynamic environments that are constantly needing to adapt to the ever-increasing cargo volumes, and this requires planning and testing of changes to their layout, workflows, and infrastructure. This can be very costly and disruptive to do in the real world. So, absolutely understanding the complex phenomena, and even Government of India has allocated a huge budget for improving the infrastructure, modernizing the ports in India. So the problem is a major port faced increasing congestion leading to delays in container handling and ship timing. They need to evaluate potential changes to their infrastructure and operational procedures without disrupting ongoing operations. So typically my simulation methodology would include obviously the use of a sophisticated simulation package, software which can create a digital model of its operations, and the model can incorporate the data on ship arrival and departure schedules, crane handling rates, truck and train traffic patterns, storage yard capacity, and layout. Researcher ran simulation to test various scenarios, including adding new cranes and what will be its impact on the operational efficiency, changing the layout of storage yard, implementing new traffic management system, and testing changes to scheduling of arrival and departure of various transportation methods. The results could be they demonstrated the impact of different infrastructure and operational changes on throughput and the efficiency. The pod used the simulation results to make informed decisions about investment in new equipment and infrastructure, typically modernizing the pod infrastructure. Simulation allowed for the testing of many different scenarios in a very short time frame, producing data that would have been very, very costly and time consuming to gather in real world setting. In the pod were able to drastically reduce congestion and increase the throughput. The impact is reduced congestion and delays, improved ship turnaround times, increased port productivity and capacity, enhanced competitiveness, and cost saving from avoiding costly real world trial and errors. So there are a couple of contributions I have made in research using the simulation approach. The first paper I would like to mention is schedule and cost overrun analysis for R&D project using ANP and system dynamics. The Stella software package is used in International Journal of Quality and Reliability Management in year 2017, volume 34, number 9, pages 1551 to 1567 by Kumar S. and Thakkar J, myself. The another paper is modeling critical risk factors for Indian construction project using interpretive ranking process and system dynamics. The paper was published in International Journal of Quality and Reliability Management in year 2017, volume 34, number 9, pages 1451 to 1437 by Tanmay Thakkar J, myself, and Maiti J. The third research paper, which has utilized the simulation approach, is impact of risk in food grain transportation system, a system dynamics approach. It is published in International Journal of Production Research in year 2020, volume 59, number 6, pages 1814 to 1833 by Rathod R, Thakkar J, myself, and J.K. Jha. So I hope you appreciated what is simulation, what is the broader classification of simulation, what are the examples under each category, and what are the different situations under which simulation becomes the most beneficial and inevitable approach. There are various real world applications we have seen, and we have seen a case study of port logistics where simulation can significantly improve the competitiveness of the port operations as a part of this session. To conclude with my university contributions, Gati Shakti Vishwavidyalaya, GSV, is India's first and only university in transportation and logistics sector, has a unique role to play in terms of creating highly skilled manpower for all the modes of transport, rail, road, water, aviation, ports, and shipping. GSV extends programs at all levels, undergraduate, postgraduate, PhD, and executive training to enable nation's aspiration to reduce its logistics costs from present 14% to 8 to 9%. Transportation sector is a growth engine for India, which contributes roughly 6.3% of GDP of India, which is remarkable. And university offers demand-driven curriculum with a focus on all the modes of transport and all three dimensions: technology, that is infrastructure; management, that is services; and policy, that is regulation, to strengthen the ecosystem of multi-modal transportation and logistics in the country. In line with the vision, innovation-led, industry-driven university, Gati Shakti Vishwavidyalaya has collaborated with the various leading industries such as Airbus, Nippon Koi, Jacobs, Siemens, Nokia, Plaza India, Railtel, and many others to significantly strengthen the ecosystem of transportation and logistics sector. Thank you for your interest in learning the various dimensions of faculty and student development. We will keep exploring more issues through this platform for the benefit of faculty and students and industry professionals, most critical entity in the higher education system in India. Thank you very much.